Hello, this is the third video of a series on analysis of directional data. This video will cover the two-sample test of equivalent mean directions of two sampled populations. So an example that Davis gives is deals with oriented data, so it's not directional data, but orientations that have the 180-degree ambiguity. And he's looking at the directions of axial planes of major anticlines in eastern Bangladesh. So the anticlines are marked by the solid lines, and he wants to know whether the directions of the anticlines are similar or statistically equivalent to the directions of large lineaments seen in Landsat images or satellite images, and those are marked by the dashed lines. So this is a two-sample test of population means. And the null hypothesis is that the mean direction from population 1, for example, the anticlines, is equal to the mean direction from population 2, for example, the lineaments. So this turns out to be an F test, and the overall strategy is to compare the sums of the resultant vectors from each sample Now these are the resultant vectors, not the normalized resultant vectors. And we're going to compare that sum with the resultant of the pooled data set, or the length of the resultant from the pooled data set. That is, if we consider both data sets as a supersample, then we can sum the unit vectors of that supersample to get Rp, the length of the pooled resultant vector. So if R1 plus R2 is about equal to Rp, then that indicates that the vectors R1 and R2 are closely aligned. Implying that the directions of the population sampled are indeed approximately equal. So alternatively, if R1 plus R2 is a lot greater than Rp, then that's a good indication that the two resultants are oriented differently. And suggesting that theta 1 is not equal to capital theta 2. So in this first situation, I'm going to sketch two resultant vectors that are nearly aligned in the same direction. And of course, the sum of those will give the orientation of the pooled vector. And so the sum of the lengths of the two separate vectors will approximately equal the length of the pooled vector in this case. And in the second situation, if the directions are very different from each other, then of course the sum of their lengths is going to be a lot greater than the length of the pooled vector. So that's the general concept. So let me show you how to do this. First, the first thing we need to calculate the length of the normalized pooled vector, and that's equal to the square root, and then we have the sum for I equals 1 to n1 of the cosine of the angles from sample 1 plus the sum of the cosines of the angles from sample 2, and we have to square that sum, and then we have to do the same for the sine terms. So the sum of all the sines of the angles from sample 1 plus the sum of all the sines of the angles from sample 2 and we square that. And again, that's all the square root. And then we have to divide by n. So n1 is the size of sample 1. n2 is the size of sample 2. And n is equal to n1 plus n2. Now from our normalized pooled vector, we look at table A9 and find the probable concentration parameter for our pooled population. That's kappa. And then for kappa, if kappa turns out to be greater than 10, then we compute an F statistic where F is equal to the total number of measurements of both samples minus 2 times the length of the resultant vector 1 plus the length of the resultant vector from sample 2 minus the length of the pooled vector. So that's where we're comparing the sums of the two resultants with the pooled resultant. And that's divided by n minus R1 plus R2. And the length of the pooled vector is, of course, the length of the normalized pooled vector times the total number of samples from both data sets. Now, if we find that kappa is less than 10 and greater than 2, then we use a more accurate equation for F, and that is F equals 1 plus 3 over 8 kappa times n minus 2 times the sum of R1 plus R2 minus the length of the pooled vectors, and that's all over n, again, n minus R1 plus R2. Okay, so once we determine kappa, we use either one of these equations to compute F, and our critical value of F, well, so if we find that if F exceeds our critical value, and our critical value being defined by our significance, alpha, 1 degree of freedom for the numerator and n minus 2 degrees of freedom for the denominator, then we can reject our null hypothesis. Reject the null hypothesis that the direction of our sampled population 1 is equal to the direction of our sampled population 2. So that was our null hypothesis that we reject. That is to say that R1 plus R2 is too much greater than what it should be if the two sampled populations had equal mean directions. And that's why H0 is rejected. So let's go back and look at the example provided by Davis. So here I've plotted polar histograms for the anticlines and the lineaments. And the first set of plots has just so all the original data. So this has the 180-degree ambiguity in it. So you can see that the anticlines, these solid bars, tend to be oriented sort of north, northwest, south, southeast. And indeed, the orientations shown by the polar histograms are in that direction, but we have some angles that are, of course, 180 degrees away from each other. So I went through method 1 and doubled it and subtracted 360 from the angles that were exceeded 360, and I got this distribution. And that method is valid, again, because all the original angles are defined to be greater than 0, and the total spread of the orientations is less than 90 degrees. And I did the same for the lineaments, and I got these orientations for the lineaments. And so using these data, I calculated R1 and R2, and I got the following values. So R1 is equal to 30.91 for the anticlines. R2 was equal to 37.92 for the lineaments. And for comparison, N1 was equal to 32. And so again, I'm summing unit vectors, and if all the vectors were perfectly aligned, were perfectly parallel, then R1 would equal 32. But R1 is less than 32, indicating the spread that we see in the first set of measurements. N2 was equal to 40. So again, the length of R2 is less than 40, indicating some spread in the orientations of the lineaments. I found that RP, the normal RP bar, was equal to 0.934. And if we look at table A9, so the normalized value is about between 0.93 and 0.94. So the kappa value is between 7.43 and 8.6. And I just did a linear interpolation to find out what kappa was. As you can see, for high values of R, kappa starts changing a lot. So in this range, it might be good to improve your accuracy if you did some sort of interpolation between those points. And I found that kappa is equal to 7.87. Our P was, again, our P bar times N, and that is equal to 67.23. And so here, kappa was indeed greater than 2 and less than or equal to 10. So I had to use my second equation for F, which had a function of kappa as the first term. So the numerator again is proportional to the difference in the sums of the two vectors, the sums of the lengths of the two vectors, and the length of the pooled vector. And the numerator is n minus r1 minus r2. And I found that to be 36.77. And my critical value for F, and I used the 10% significance, and that is 2.78. So indeed, F is greater than 2.78. So the null hypothesis was that the anticlines were, on average, the mean orientation of the anticlines was equal to the mean orientations of the lineaments, but this test shows that H0 can be rejected. The lineaments and the anticlines are oriented, have different mean orientations. Oh, and I'm noticing I need to write this equation for F more clearly. The kappa is in the denominator of this first term for F. So this is 1 plus 3 over 8 kappa. Okay, well this concludes this series of videos on directional data.